Hello everyone, welcome to my presentation. My name is Mojtaba and I'm a PhD student in Biomechanics section at KU from Belgium under supervision of Professor Lisbeth Giris. This presentation will be related to a parallel finite element implementation and reaction diffusion system in which we have also a moving boundary, and as a use case I will present my PhD work on simulation of biomaterials degradation. So first couple of slides on the statements of need of the research. Talking about biodegradable metals, the most famous ones are magnesium, zinc, and iron. And the main advantage of using biomaterials, these kind of biomaterials, is that they can gradually disappear and get absorbed in the body, so there is no need for a revision surgery to remove them, and they can be replaced by new tissue that is formed or new bone, let's say. And they have great mechanical properties because they are metals and they have positive contribution to biological aspects of the body, like the human body metabolism. But still, their controlled release profile has remained a challenge, especially regarding the fact that they have various applications inside the body. So the degradation profile should be optimized and tuned for various applications. So the main challenge is tuning the biodegradation rate to the rate of regeneration of new tissue or new bone and optimizing the implant design. This can be solved. Actually, these are solved in this project. A solution is proposed by a mathematical model of the biodegradation process that can be accompanied and coupled by other tissue engineering models like tissue growth models to simulate the regeneration of new tissue and bone, and also by considering the environmental effects. So the workflow of this project is underlying phenomena are converted to mathematical models and the mathematical models to computational models. The underlying phenomena are the chemistry of biodegradation, the physics of perfusion, which is actually fluid flow inside bioreactors in which we want to study the cell growth and cell culture conditions, and also biology of tissue growth. And mathematical models are actually partial differential equations. Let's say the most important of which are reaction-diffusion convection equations, Navier-Stokes equations, and also level set method and phase field for tracking the moving interface, which is actually one of the main let's say, novelties of this work, to model the corrosion or the tissue growth as a moving boundary problem. And for computational models, it's actually a combination of finite elements model and finite difference method, as well as parallel computing libraries and open source solvers. So the chemistry, the first step is actually knowing the chemistry of biodegradation. It can be, a little bit complex. This is behind the scope of this presentation. But the model should capture some simple steps of this complex phenomena, which is actually the dissolution of metallic implants and a formation of a protective film on top of it, as you can see here. The effects of various ions in the medium, which differs from electrolyte to electrolyte, and also depends if this is an in vivo or in vitro investigation, and also side effects or side products, such as formation, such as change of pH in the environment. In order to convert the chemistry, the described chemistry, into mathematical forms, we use, this interaction should be converted to mathematical forms. So we use reaction diffusion convection partial differential equations. And as an example for just the magnesium ions transport, this is how the equation looks like. So it comprises of the diffusion term, how the magnesium ions diffuses through the medium, or other components, how they are convected by an external velocity field, and how they react with other components. But as I said, the moving boundary is quite important in this work to compute the mass loss and study the change of morphology of the objects, of the implants and medical devices. And in order to do that, we implicitly track the moving corrosion front. And in order to do that, we take advantage of level set method, which is a very nice and quite advanced technique to formulate moving boundary problems. But in order to determine the velocity of the interface, which is required for the levels of formulation, we have a look at the interface and we correlate the change of concentration of materials that are related actually to transport the mass to the velocity of the interface, and then we can in the end formulate the level set method to level set equation to be like this. So this is another PDE to solve, and here we have a find function. That concept of the find function is it divides the medium into different zones. So we have the interface where the phi is 0, so the 0 isocontour of the interface is actually of the phi function is the interface, and where it is negative it's the medium, and when it is positive it means that it is inside the block. So this is actually how we can track the change of morphology over time. In order to construct a computational model, we need to discretize the PDEs that differs, as I said, depending on the number of components that we want to consider. They can be like 6, 7, 8 equations. But we use a finite difference formulation for temporal derivatives and finite element method for spatial derivatives. And the mesh is adaptively refined on the interface because we want to increase the accuracy of the employed level set formulation. So after let's say labeling the computational domain into like the block and the medium, we refine the mesh on the interface. So generally the mesh are like this. And because of this, we usually have a high number of elements, like for example 10 million to 20 million in 3D after mesh generation, and after 4-week formulation, the degrees of freedom for each PD is 2 million to 4 million. For weak formulation, we use FreeFEM, and for mesh generation, we use Salome and MMG. And as a result of this higher number of elements, and also the complexity of the computation, parallelization is essential. And in order to do that, we take advantage of high performance domain decomposition technique, and also high performance preconditioners and solvers. And also the parallel post-processing also performed in a parallel I/O approach. So for the level set implementation, there are a couple of problems. First of all is the penalization on the boundary conditions, because the main boundary conditions of the work are applied on the interface, which is a solution of another equation. So boundary conditions are applied on a solution of one of the equations. And also the problem of concentration oscillation, because we have like a jump on the material properties, or also material concentration on interface. And for overcoming this, we used a mass lumping technique in FreeFEM. And also, as you may notice in the level set formulation, one of the terms are the gradient of concentration on interface, and computing this can be quite challenging. So that's because of the concentration oscillation actually. So in order to do that, we compute a minimal distance of h, and then we go above the interface and we compute the gradients there to avoid the oscillation. This is one of the most important tricks that we use to compute the gradients on the interface, on a moving interface. And then problem of redistancing the distance function, because it is actually in parallel and in partition mesh, so the redistancing can be a little bit tricky in general. And because as I said, we want to consider the effect of hydrodynamic conditions and the effects of fluid flow. We need to consider the convection effect, and adding fluid flow it increases the complexity of the system, because we need to deal with the Navier-Stokes equation. And we were, in order to increase the performance of the code regarding the high number of elements that we have, and also the cost that associated with it to store it on a disk and then solve it with another CFD code, we decided to implement our own parallel fluid flow code in FreeFEM with very effective and high performance preconditioners. But then another challenge was to compare the output of the code that we have developed CFD in-house code with OpenFOAM to make sure that it is totally correct. I haven't put the results of this comparison here, but this was totally verified. For the simulation results, just to show you what I'm talking about, this is, for example, an orthopedic screw degradation. As you can see on the left, it is the degradation of the screw and release of material. And on the right, this is just a zero ISO contour of the level set function, phi function. So this is how the results look like actually, and this is for a degradation of a tissue engineering scaffold, porous scaffold. On the left, you see the formed protective film on the interface of these scaffolds, and on the right, degradation as well as the zero ISO contour showing the change of morphology over time. And this is for a jawbone plate, for degradable mandible plate implants. So this is how as I said, the material releases and how the implant starts to degrade. And also for a narrow cuboid that we use to validate the model from a set of corrosion immersion test for magnesium. And these are actually the same results, but post-processed in 2 different ways. And also quantitative results, change of pH, and also formation of side hydrogen products, for which from which we use to validate the model, and also to also perform parameter estimation. As you can see, there is a good agreement between the experimental results and computational predictions. And this is the degradation with fluid. So if we have a fluid flow in the direction from left to right, you can see that we will have directional degradation, showing that multiphysics formulation of a problem works very well in this setup, that the flow is coupled with the reaction diffusion system. But also, elaboration on the high performance computing aspects of the work. So the first thing was actually distributing the mesh among available resources, so mesh partitioning. And for doing that, we use high performance mesh decomposition. The method was called overlapping short method, available in HPDDM package. HPDDM actually open source library. And then another aspect is solving the linear system derived from the finite element formulation. And in order to do that, we had a set of very effective preconditioners available in PETSI, such as Boomer AMG, available from the hybrid package for reaction diffusion systems, field split preconditioner for fluid flow, as well as a set of iterative solvers such as GMRS. So for the domain decomposition, as I said, it was decomposed using overlapping techniques, overlapping Schwarz preconditioners. So the mesh is overlapped, and each partition is assigned to one MPI process. And for performance analysis, we had some deep performance analysis from different specs of the works, and they're published in the journal, International Journal of High Performance Computing. So a setup with a ticker block was considered in this work, and only 3 PDs out of like 7, 8 were solved. And the degrees of freedom, so this was not actually a very big problem. Degrees of freedom was around 150,000, and the elements were around 1 million. But for parallelization benchmark, we had weak scaling, so doubling the problem size while doubling the resources, such that, as can be seen here as a sample demonstration, we have the problem size and the mesh partition. So as we double the problem size, we also double the available resources. But also strong scaling, in which we keep the problem size constant and we double the resources. So for the weak scaling, these are the results for simulations on for example, a demonstration that you saw in a previous slide, and these are the speed up and pair efficiency computed for each simulation. And using Gustafsson law, we were able to correlate the speed up to the parallelized portion of the code, and according to this, 82% of the code of the techniques of the implementation was capable of being parallel. And also for strong scaling, these are the results that are run up to 300 cores. That was actually, it was because of a set of limitations that we had in our research institute. But yeah, in the future, we will definitely run this on higher number of nodes up to, for example, 10,000, 20,000, to be sure that, yeah, this implementation is scalable, but also the same set of results for speed up and parallel efficiency, and then Amdahl rules were Amdahl law was used to correlate speed up to the parallelizability, and according to this, 99% of the code is able to run in parallel. And also another thing that we did was comparing the preconditioner and actually the solver performance for various available preconditioners, iterative solvers, and also direct solvers. And according to this, as I said, the iterative solver GMRES and also the Heap-Rip Boomer AMG showed the best performance for the reaction diffusion part. And also a couple of slides on the software development and open source aspects of the work. The software that we have developed, actually we transformed all these developed models, computational models, to a multifunctional 3D simulation code. And the code features a cross-platform customizable user interface that includes also pre-processor and a relatively basic post-processor as well. So the code is a sort of, we can say that it has a FreeFM and PETSI backend and Qt and C++ front end. And the whole project is available as an open source software to anyone who is interested in this. And all the employed tools are open source. So all the tools that we have used for mesh generation, also design and solving, partitioning, post-processing, user interface design, and preconditioning, they are all freely available. And it means that the results that we have obtained can be reproduced by anyone on the planet, and they can easily grab the code and start to use it or develop on that or whatever else, just to evaluate it and so on and so forth. And all the codes developed are hosted on GitHub. So the core of the simulations, the computational models are available, as well as the UI and also the preprocessor that is developed by FreeFM and ParaMMG for parallel mesh generation and parallel mesh actually partitioning, and documentations, and also the coupled flow code is a sort of diffusion convection code in parallel. They are all available on GitHub. And as a final note, I'm interested to also announce here that I have started a project on YouTube, actually, that is related to sharing experiences on scientific computing using open source tools, to showing the power and freedom that these tools will have in scientific computing and high performance computing. And this project will aims to provide insight into the details of these techniques and showing that they are not as complex as they seem. So, and any contribution to this project is highly welcome from anyone interested. Thank you so much for your attention.